Thank you, everyone, for coming. Appreciate having you here. So we're here today to talk about a tool that we created called CALDERA that automates adversary emulation. So I'll introduce what that means in just a minute. But first, I want to tell you about who we are. So my name is Douglas Miller. I'm a researcher at a company called MITRE that runs research and development centers for the United States government. I'm a senior cybersecurity engineer, so if you've heard of ATT&CK, that's ATT_CK. That's a threat repository that we made at MITRE. I worked on that. I also do a bunch of applied red teaming in my day job as well. And I'll let my colleague Andy introduce himself.
Can't hear me? Testing, 1, 2. Sounds like you can hear me. Okay. My name is Andy. I also work at MITRE. I work on ATT&CK as well, and also some AI research. I'm really bad at BIOS. Doug?
Okay. So with that out of the way, what is adversary emulation? It's a term that we use within MITRE, but I didn't know if it's a term that other people understand, and Google tells us that pretty much nobody uses that term. So I'm going to tell you what it means. But first, I want to introduce you to the problem that we're trying to solve. And basically, the problem is the false negative problem. So if you're like me, you're thinking false and negative and like going through the mental math of like true positive, okay, false positive, false negative. False negative, let me help you out. A false negative is the stuff that you should have detected but didn't. So as a network defender, this is like the stuff that bad guys do that you have no visibility over. And the idea here is you want to detect that stuff, right? And I mean, so let's, like, quick show of hands, who here is confident that they can detect every single attack possible against their network? I mean, so no one raised their hands, right? And I mean, if someone did raise their hand, I would want whatever they're doing. Because that's kind of like the panacea, right? I mean, everyone knows we're vulnerable. So if you think about like other domains, not just cyber, this is somewhat of a solved problem. So in a previous life, I worked at an electronics company, and they have a big lab at the company I used to work at dedicated to just stress testing devices. So they'd have a machine that just pressed a button millions of times to see how long it would take for that button to fail. And most organizations don't really do that. I mean, it's a hard problem. Cyber is much more complicated than just pressing a button. But this is the best way to tell if you're safe, is by testing your network. And that's the idea behind adversary emulation. So you introduce a realistic adversary, so it's something as real as you can make it, onto your network and see how far the attacker gets. Ideally, you control the adversary. You don't want to take a real adversary and put it on your network, but you can hire a bunch of really smart humans to do it, or use a tool like CALDERA. And think about this for a second. So if you have an adversary, you can actually see, how far did the adversary get? Were they able to move from my endpoint workstations to, my like core enclave? Did I detect them? Did I not detect them? And then you can sort of, peel back the curtains and think about what mitigations you could put in place. How can I prevent this in the future? And how can I improve my detection? So this idea kind of works in a cycle. So it's not good enough to just do this once. I mean, it's like any other thing. It's like penetration testing. It's like vulnerability scanning. You can't just do this once. You have to keep doing it over and over again. So you start by emulating the adversary, right? And then you kind of do some inspection. So did we succeed? Did we detect? How can we improve? And then you go back and you think about what changes you can make to improve your network. And so CALDERA, the tool, really is just a piece of this puzzle. The rest of this is something that you have to do as a human, as a network defender. So there are a couple of key pieces to making adversary emulation work, and I already talked about a few of them, but you really need to make it as realistic as possible. You want the adversary to be like a real adversary. And this is different from a lot of other testing mechanisms. So you think about vulnerability scanning, you think about penetration testing, even red teaming, if any of you are familiar with that. Red teaming, for example, you're really looking at trying not to get caught. So if you're a red team, you don't want the blue team to catch you. That's not what adversary emulation is. If the blue team catches you, that means good job for the blue team. What's important is you want to be real. You want to use the same techniques, you want to use the same tactics, you want to use the same tools as what attackers are going to use on your network against your organization. You want to be end-to-end. And this is a big one. So this really differentiates it from something like pen testing, where you're really just looking for those perimeter holes in your network. With an end-to-end adversary emulation, you get in, and that's just the start. You want to go all the way towards whatever the full compromise is for your network. So compromising the domain controller, getting domain admin, exfilling the critical data off your network. That's where you want to stop. You want to do the whole spectrum. And you want to be repeatable. So you don't want to just do this once. You want to be able to do it multiple times and measure the improvement in your security posture as you implement mitigations and try to improve your security. So this is the tool. It actually exists. I know I've been kind of talking high level and introducing the concepts, but I want you to at least have a mental picture for what we did while we're talking about it. So this is the operations screen. This is kind of like the core piece of how it works. So there's a lot going on here, and we'll dive into it. But you have a picture of your network. The bubbles here are the different computers that are taking part in the exercise. And then you've got kind of a running screen on the right-hand side of everything that the system's doing, all the steps that it's taking. So kind of an overview of how the tool works. So the first thing you do is you install a small service shim on every computer that you're going to be using to participate. So this is just a small Windows program. The system itself is Windows specific. So unlike you learn in university, most of the world still runs on Windows, sadly, or not sadly. But so it is Windows specific. You install the service shim. You create an adversary by giving it capabilities. So these are things like privesc, WMI, lateral movement, exfil, and then you just basically click go, and the system knows how to compose the pieces together that you tell it to do. So while the system's running, it'll tell you what's going on, it'll say what it's doing, and afterwards it'll kind of show you an overview of what happened. And it does have a cleanup function, so anything that happens in the network, files that are dropped, processes that are created, services that are created, all that stuff gets cleaned up. Most people want that. So there are kind of three key components to designing a system that automates adversary emulation. And the first one is what the adversary is able to do, so the feature set that the adversary has. And the thing that we used is something that we also created called attack, so of course we used it. But it is actually a really good model. Andy will talk about this in a minute. So another piece of it is not just what the adversary can do, but how it can do it, so the choices that the adversary makes. And this is a really interesting, really fun problem that we worked on. And the last part is sort of all the extra stuff. So all the glue, the stuff that parses command line output, all that fun stuff. So we did all three of these things, and we'll talk about them in detail. Oops. So with that, I'm going to hand it off to my colleague Andy for the adversary model.
You guys hear me? Yep, cool. Thanks, Doug. Yeah, so I'm going to talk a bit about the adversary model first. When we were designing CALDERA, we see a lot of terms like red teaming, pen testing, things like using exploits or vulnerabilities and configuration, simulations, all very useful tools. But when we were designing CALDERA, we didn't necessarily want to go that route. We wanted to focus on adversary emulation and using kind of showing what a real adversary would do after they get into your network, really focusing on that post-compromise aspect. So this led us to use the MITRE attack framework. I'm not going to go through it in detail, but it's essentially a higher fidelity model that focuses on kind of what the adversary does after they exploit and they get into your network. Laser pointer doesn't really work, but it's all publicly available online, attack.mitre.org. It's awesome. I recommend it for almost everything. But we've basically taken the right of exploit kill chain phases and broken them down into 10 high-level adversary tactical goals. The persistence, privilege escalation, defense evasion, lateral movement, exfiltration. All those kind of normal things you read about adversaries doing. And then we enumerate the techniques that are available to the adversary to achieve those tactical goals. So as an example, if you look second from the bottom upper left-hand corner, legitimate credentials is a way an adversary can use to maintain persistence or privilege escalation or even defense evasion. One of the key features of attack is that everything in the model, all these techniques are backed up with real open source intelligence. So we've identified publicly available threat reports to say, hey, adversaries actually do these things. These are the things that they actually do. And that's been useful for CALDERA because we want to focus on that real component of emulating a real adversary. This is a brief enumeration of the things that are currently encoded into CALDERA based on attack. We have persistence, privilege, escalation, defense evasion, execution, exfiltration, discovery, kind of the main things that you need to emulate that full adversary lifecycle. So I'm going to switch gears a little bit and talk now about the decision-making component. And when we first made CALDERA, we took a finite state machine approach where we would basically scan for hosts, we would select a target, we would scan the target, move laterally to that target, and then dump credentials. And this worked well, it was successful, it went through, it kind of iterated through this process, but there were some downsides. First, it was hard to add new techniques. Every time we wanted to add something, we had to fully recompute the finite state machine. If I want to establish persistence, where does that fit in with relationship to all the other actions I have? It was also very hard to configure an operation to be specific. If I want to pick and choose which one of these actions, how do I make sure that the finite state machine that results from it actually works? Then the other downside was it was very predictable when it was executing. It would just keep running through this loop repeatedly. You can see in this visualization, I don't know if it renders too well on the screen, but CALDERA just kind of iterated through there over and over and over again. And if I'm a defender, and I'm seeing something that might look like that, it's a little easier to detect than something that's doing a little bit more to blend in. So we decided to go to the drawing board and consider, okay, how do we actually design this decision-making engine? And we thought to ourselves, okay, humans, we typically have, lots of this domain knowledge, domain inference. We're looking at things, we're kind of guessing things, we're doing targeting, TTP selection, all of these things. Do we dump creds or do I launch an exploit? What's the right technique to use in this specific situation? And all of that stuff, we need to automate it as CALDERA. So we came up with some requirements. We want to make intelligent choices for our adversary. We want to achieve tactical objectives like an adversary does. We really want to easily incorporate new techniques. I don't want to have to recompute a finite state machine. I just want to make a new technique, throw it into the system, and let it go. I also want to work in new and unknown environments. By that, I mean, I don't want to have to configure CALDERA and say, okay, these are the hosts that are on my network. These are the credentials that are on my network. These are the shares. I don't want to tell it any of that. I want to tell CALDERA, okay, it's installed. Go have fun. Go be an adversary. I also want to vary the operations, and then finally, I want to chain weaknesses for maximum effect. What I mean by that is I don't want to just pop a box. I want to take a little vulnerability. Maybe I get some creds, and then I can mount a file share, copy something over, and then execute that remotely. Chaining these little things together that create a larger attack pattern. So to kind of motivate some of the things I'm going to talk about, I'm going to take a very, very toy, simple example. Let's say you got host 1 and host 2. I've got a rat running on host 1. I've identified that there's some sensitive files on host 2, and I want to exfiltrate them. So I might have this this bag of TTPs exploiting a vulnerability, mounting a file share, copying a file, remote desktop. The question is, how do I arrange these different TTPs into my goal? How do I chain them together to exfiltrate data? So let's look at a specific example of an action. Here I want to talk about copying a file from host 1 to host 2. What we might want to do in understanding this action is enumerate what the requirements are. And here the question is, well, what do I need to do to copy this rat file over to the other host? First, I need a working rat on the source host, on host 1. I need a mounted file share from host 2 onto host 1. Then I need write access to that file share. A little more technically, we might call these requirements the preconditions of the specific technique. And then the question is, what happens after I copy this rat file over? Well, there's going to be a new file on the target host, and that file will contain the rat. Again, more technically, I might call these the post conditions. And so the idea, one of the main ideas of CALDERA, and I'll go into this later again, is to take these techniques and decompose them into their preconditions or their requirements and their post conditions, which are their consequences. What's nice is I might say, okay, let's say my goal is over here on the right to copy a file. I'm going to get that file on the target, which is my goal. That's what I'm looking for. In order to execute copying a file, I need a mounted share. Oh, look, I can take mount share as another action. And the consequence of mounted share is getting that mounted share. So if I mount the share, then I can copy a file. But to mount the share, I need credentials. So again, backward chaining it back. Again, say, okay, if I dump credentials, I'm going to get those credentials that I need. And so to jump into this chain, I just need an elevated ret running on host 1, which is what I started out with. Again, more terminology. We might call this sequence of actions a plan, which is basically just kind of these actions together that, again, we have the preconditions and the postconditions that kind of make them logically flow. So this is kind of the core Caldera idea. Instead of prescribing explicitly what we want the decision engine to do, we're going to move towards something that's dynamic and model-based. Essentially, we want to tag every single action, all of our techniques, with the preconditions, which are the requirements, and the postconditions, which are the consequences of executing a technique. Now, I no longer need to explicitly tell Caldera what it needs to do. Instead, it can compare what it knows about its current state to the preconditions of its available actions, and then it can determine which action it should execute. As an added bonus, by having preconditions and postconditions, I can now plan for the future. If I dump credentials now, that will help me execute lateral movement sometime in the future. So it's not a presentation if I don't make a forced chess analogy, but in chess, we kind of also have a little bit of preconditions and postconditions going on. Here, from a precondition perspective, we can essentially use the rules of the game, based on how the pieces move, as the preconditions, along with the logical, invariance of the game. Here we can see that rook is in check, and that's a requirement that I have, that the king has to get out of check. So I can either move my king to the right or interpose a piece in front of the rook to stop the check. From an emulation sense, we might say, given an escalated foothold, I can dump credentials, I can add or modify registry keys, I can set up scheduled tasks, and do all sorts of fun stuff. Now, postconditions can tell you what happens after doing something. In chess, we might say, okay, if black moves the bishop over there, then white might take the queen, and then black will take the bishop. King moves over, and then the knight puts the white king in check, and black is Bobby Fischer, so it's all fun and games. From an emulation standpoint, what we can essentially do is start chaining actions together towards achieving something. We dump credentials and we laterally move. We might add or modify registry keys and then dump credentials. We essentially construct a search space of all the possible plans and all the possible actions. So jumping back to the running example, how do I go back from host 1 to host 2? Well, the idea is, again, I can chain these actions together. So here's an example plan where I'm using copy file to move laterally. First I dump credentials, then I mount the network share, then I copy the file, remotely execute it, and then finally, now that I have code execution after the remote execution, I exfiltrate data from host 2. Another plan is I might want to just immediately jump the gun, exploit a vulnerability from 1 to 2, and then exfiltrate data. Then another plan might be I'm going to dump credentials, then I'm going to use RDP, then I'm going to exfiltrate data from host 2. So the question is, okay, I can enumerate all these plans, look ahead in the future, find all these things that achieve my goals, but which is the right plan to execute, or rather, which is the first action to execute? And what we did is we designed a Caldera heuristic. Essentially, we assign each plan a score based on the reward of the actions in that plan. And that score is kind of a summation of the weighted rewards, preferring to achieve the goals earlier than later. So in this example, I might say, okay, I love exfiltrating data. That's going to get a reward of 100. I like dumping credentials. It's not bad. I'm going to give that a reward of 50. It's not as good as exfiltrating that data, but those credentials might be useful in the future, so that's going to get a 50. Copying a file is fun too. It's not as good as creds or exfiltration, but I might assign that 5. And then everything else, I don't really care about it. Those are all means to ends, so I'm going to assign them all 1. So with that all said, plan 3, using RDP for lateral movement, kind of becomes the best choice, because I'm dumping creds right away. I'm using RDP, which I don't really get a reward for, but then I'm achieving my goal. If you compare that to plan number 1, I'm dumping creds, which is good, but I'm not exfiltrating data until much further down the line. I have to do a lot more things to actually get to that point. And then plan number 2 is exploiting a vulnerability, which isn't very worthwhile for me, and then exfiltrating data. And so when you kind of compute all the rewards and the scores, plan 3 becomes the best. So the next thing we need with Caldera is a data model to talk about the preconditions and postconditions. It's easy for me to kind of verbalize them and say, I need this and I need that, but we need a way for Caldera to do this all automatically. So Caldera's language basically has objects and type fields, where the objects reference kind of common Windows things, as well as other things that are more useful for the adversary. I'll give a couple examples of that. And then the other thing is that fields specify the properties of the objects, and then we restrict that by type. And again, I think it's better to walk through with an example. So here's an example host object. On the left, you can see we have host, that's the object type. Host has 8 different fields. You have the fully qualified domain name, which is a string. You have a list of admins. That's a list of type list, host name, DNS domain name, again, strings, all these different things, and OS version, which is just a reference to another object in the data model. As an example host, we have the fully qualified domain name of PC1234. The admins are Andy and Doug. The host name is PC1234, and so on and so forth. And this kind of breaks down the entire model. It's a little, or this is the majority of the model. You can see on the bottom there's like +7, +11. But you know, the things that we have here though are kind of common things that we tend to talk about, like scheduled tasks, services, processes, registry keys, users, shares, files, hosts, all these fun things. And then within each, you have the fields that Caldera cares about. Some of these are a little more specific for Caldera's execution, like time delta measures the difference, the time difference between two hosts, and we actually have an object to represent that. So we have a data model, that's awesome. Now we need a syntax to actually declare the actions, and so Caldera also has a syntax with which we describe the preconditions and postconditions. We have preconditions, postconditions, a not equal invariant, and then pre-properties and post-properties. To be very honest, it's a little confusing. We have documentation that is available online that can describe it a little bit better, but I just wanted to flash real quick, say that there is a syntax, it works, but if you're interested, we have more stuff online. So bringing everything together, we kind of have a 5-step plan. I know I have a 6-step listed there, but we update the world state and figure out what we know, what is actually true in this environment. Then we use the preconditions to figure out all of our valid actions that we can execute in this current time step. Then we construct plans that lead off with those actions. So I again look towards the future and chaining actions together with the preconditions and the postconditions. Then I run the heuristic to determine the best plan out of all the plans that I identified. And I execute that first action in the best plan. And last, I repeat. Observe the responses, kind of jump back into this cycle and go through as I compromise the network and achieve my goals. So that's it, we're done. Preconditions and postconditions, you know, we can dynamically construct plans. We can construct them to make intelligent choices. It's easy, very easy to incorporate new techniques. All we have to do, define the preconditions, define the postconditions, define technically what you need to execute, then you're done. You just throw it in there, it figures it all out, it's perfect. We can modify the rewards as well as the actions we want to have in the operation, and that can help us vary what we're doing. We can chain weaknesses together because we have the preconditions and the postconditions. Then we can function in new environments. And there's an asterisk there because, well, that's actually a little harder said than done. It turns out doing this deterministically is kind of hard. Sometimes when I dump credentials, I'm going to get very useful credentials. I might land on a box and dump credentials and, oh, it's a domain admin, that's wonderful, I'm basically done. Sometimes I might land on a box, dump credentials, and find credentials that are completely useless. So when I'm constructing plans, it turns out this can be kind of disruptive because I don't know exactly what the outcome of some of these actions might be. And in reality, handling uncertainty is a very, very difficult problem. And we have a couple of papers that are available on some of the ideas that we've considered, some of the things that we're doing. And those are also available. And if you're really interested in this, I'd recommend, in this problem, I'd recommend this paper by Jörg Hoffman, which kind of decomposes this entire problem of using planning for red teaming based on the action model, which is whether or not actions can remove information from your knowledge base, well as your uncertainty model, which is whether or not you can fully observe the network. And we kind of lie somewhere in the middle of there, but long story short, we have our own approach, which is a very quick fix with something we call hints. Essentially, if we can't predict the outcome of an action, we have a somewhat hard-coded field that provides a hint to the planner as it's chaining the actions together to figure out what the outcome might be. And in our case, right now, what we're doing is we just have the best outcome as the hint. So I don't have a great example here, but if you look in and see this as like the state search graph, if I start out and try doing everything deterministically, I might only be able to identify this one top plan. If I have hints though, I can then say, okay, maybe I have these other outcomes of this first action, and that's going to lead to these other potential branches. And chaining that again further, we can start constructing a much larger search tree. So what CALDERA does is it's able to do this internally as it's choosing an action. It'll execute this first action, observe the real responses, then update its knowledge base, and move through whichever is actually corresponding to what's going on in the real world. I think with that, I will give it back to Doug. Thanks.
So if you're more of a software programmer like me, this is the section you'll care about. So this is more of the architecture and how the tool is constructed. So this is a very general overview of the software. We have a server component. That's the thing that makes decisions. All the planning that Andy just talked about happens on the server. And the server makes connections to all the clients which are running on systems that are partaking in the emulation exercise. So you can see there are a couple components in the server. There's an HTTP server, which you can access as an administrator. There's a nice little web interface that I showed you before that you can kind of see what's going on. You can configure everything. There's a database under the hood that stores everything. We have the planner and the execution engine, which is kind of all the extra stuff that ties everything together. On the clients themselves, there's a service that kind of keeps track of all the bookkeeping. So I mentioned that the operation can be cleaned up automatically afterwards. That's the job of the service. In this picture, it's called the agent. And we have rats. So the rats are the things, the pieces of software that actually do all the running of the command lines, all the emulation bits. So the system itself, written in Python 3. The rat is written in C#. The database we use is MongoDB, web interface is JavaScript. The logic, which is sort of the underlying implementation of the preconditions and postconditions that Andy talked about, that's all written in a language called PyDatalog. That's very interesting, but it's outside of the scope of this talk. But if you're interested in that, come talk to me and I'll give you an earful about that after the presentation's over. Probably the moment that you've all been waiting for, the demo. And we have a live demo, so hopefully everything works. I know that's a little bit crazy. So just bear with me as I get that set up. So this is the software. Oh, that's not the software. Oops. Try again. Okay. This is the software. We have a small network running locally on this laptop. So we have a domain controller and 4 hosts, right? 4 hosts, 4 Windows 8.1 machines. So I'm going to just kind of breeze through this, but we'll take a look. So these are the adversaries. These are like the core building blocks of how you configure Caldera. So we have a few built-in ones. I made a special one for this presentation. It's called Advanced. And these are the 8 or 9 different steps. So it'll be able to dump credentials. It'll do a bunch of different discovery steps. So it'll query for local administrators. It'll dump computers. It'll get information about the domain. It can do privesc. So we've purposely configured the starting system to have a privesc vulnerability. Yeah. Oh, yes. Thank you. All right. Is that good? A little bit more, sure. All right, hopefully that's big enough. Not everything will fit on the screen, so I'll just have to scroll. It can do service, local privesc. We have purposely configured a service that's vulnerable to this. So the service, I think we made it so the binary is world writable, so you can overwrite the service. So Caldera will be able to do that. if everything goes well. And it can do lateral movement. I think we have passed the hash copy and WMI for lateral movement. So that's what the adversary looks like. So I'm just going to go over here and I'm going to create an operation. And let's see, give it a name. So I'll name this Black Hat 2. The adversary we're using, these are the adversaries. I'll pick the one that I was just showing you. We can also select a network. In this case, I'm using the demo network and the starting host. And then there's some sort of startup options here. So because you you need a way to kick off the operation, Caldera has a built-in feature to just spin up the first rat automatically. That's kind of like cheating, but if you think about it, it's sort of the equivalent of like launching a spear phishing email and have someone click a malicious document. So if you select the bootstrap option, which is what I'm going to do just for sake of time, it'll spin up the first kind of patient zero rat automatically. And there are a few more configuration options here, but I'm going to select the active user as the initial context. So this is an unprivileged domain user, not the admin on the first system. Whoops, we'll hit go. And if everything goes well, I'm going to zoom out here because it doesn't fit well on the screen zoomed in. So you can see there are bubbles and colors. So the bubbles represent the hosts. The colors will change as the status of the operation changes. So one of them is yellow. That's the starting host. And yellow means it's an unelevated process. Blue, in this case, means that Caldera knows about the existence of the other hosts, but doesn't have anything running on them right now, so that they haven't been laterally moved to. So you can see on the right-hand side, it's doing some things. So the bubble just changed to red, so that means privesc occurred. You can see it looked for privilege escalation vectors right there, and then the next step, it attempted to escalate, which succeeded. So I'm going to scroll down here so we can keep seeing what's going on. So it dumped creds after that. It's doing admin enumeration right now, so it enumerated administrators of 8x01. It used pass the hash copy to move an implant over to 8x02, and now it's executing that, which succeeded. So it's dumping creds now on 2, and it's pretty much going to keep going at this point if everything is going well, and it'll migrate its way through the network. One of the things I didn't mention is, and you can't really see this from the visualization, but the first host that it started on, 8x01, had 2 accounts on it. Or actually, it was just 1 account. Yeah, so it had 1 account, so it got creds on the first host. And then when it moved to 8x02, there was another account that it found, and so it used that account to move to 3 and 4. And the reason it needed to do that is because the administrators were configured differently. So it's complete. And now it's doing cleanup, so everything changed back to normal because it's deleted everything. Yeah, it's done now. So we can see, so this description here is just a very high level description. Each of these boxes represents an individual step. So we can click on one of them to get more information. What's a good one here? Let's do one of the cred ones. Yeah, so let's look at Mimikatz. So you can get information. We've used attack. So everything in attack, Andy mentioned, there are techniques and tactics. So we have those configured. So you can see sort of at a high level what this step is. And this is the actual command line that was executed and the standard out. So if you're familiar with Mimikatz, this is Mimikatz output. So this is going to give you all the stuff. There's the password right there. This is a fake domain, so don't worry. So I'm going to show you now one other thing. I'm going to kind of highlight the positives of using a non-state machine-based model. So I'm going to just change some of the techniques that the adversary uses. So if I go back and I'm gonna edit this adversary. So this was the adversary we started with. I'm going to hit edit, and I'm going to make a couple changes. So I'm going to start it off this time as a system, so as an elevated process, but I'm just going to leave the privesc options in there. So you'll see it doesn't need those, so it doesn't really matter if I leave them in. The system is smart enough, it uses the planning to just know that that's not useful. I'm going to change the lateral movement technique. So instead of doing WMI, which is this step, I'm going to unselect that, and it's going to use pass the hash SC, which is just a different lateral movement step. It's gonna, instead of doing pass the hash copy for file copy, I'm gonna use net use, which is just a different copy technique. So for that, I need copy file and net use. So I've done it, I've submitted, and then let's go back and run another operation. So, right, so everything's gonna be the same except I'm going to start a system now, so it won't need to privesc anymore. So there we go. So things are running. You can see it started as red. It discovered these other systems after it did the first step here, enumerating all computers. And it's just going to, if everything goes well, it's just going to keep doing its thing. One of the interesting things, as Andy mentioned, it operates with zero prior knowledge. So everything that it does in this operation, it's all the information that it gathers is sort of siloed off. So it's not using anything that it discovered in previous operations in this one. That would be kind of like cheating, I guess. So it's everything that it's doing fresh, as if it just stepped onto this network for the first time. So it's kind of chugging through. It didn't do the privesc. It just went directly to running Mimikatz, did a bunch of enumeration steps. It mounted the network share, and then it copied in implants, passed the hash SC, ran Mimikatz on this new host that it acquired. It's going to keep doing this same process, so it'll mount the network share, copy an implant, pass the hash SC, run Mimikatz once that completes, and it should get the final cred, and then it'll be able to move to 8x03 after that. So, yeah, I'm glad the demo worked. That was good. So as you can see, I mean, it's actually running fairly quickly, which is surprising, given like all the complexity that's happening under the hood. We can support, I think, 15 to 20 hosts roughly before the computational complexity just gets too difficult to build all the plans. So if that kind of gives you an idea of the scope of the project and what's applicable. Okay, so it's done. So let me switch back to the presentation now. Cool. You can kind of walk through like what happened under the hood during that from more of like an architectural standpoint. So we've got the architecture diagram here, and this is just going to show two hosts. So the first thing you do, you issue a start command, tells the server, please run an operation, gives it all the configuration information, and sends the first command to the agent. If you're doing a bootstrap, in this case we are, the agent will spin up a rat for you, and then that rat will check in with the agent, and the agent will register that check-in with the server, and then that updates the database and triggers the planner and the execution engine to continue running an operation. So then the rat will ask for a command to execute, and then that gets passed again through the server and makes its way to the planner. And so now the planner has to start thinking about, okay, what makes sense to run, what command do I want to issue, what step do I want to execute during this operation. And once it makes a decision, in this case, maybe it wants to do SC create, so it's going to create a service to laterally move. It'll pass that decision all the way through down to the agent, and then the agent issues that command to the rat. The rat executes it, and a result of SC create is a new rat's run on a remote host. And then it'll check in, and so this is where it starts to get repetitive. The process kind of continues. that's that's the application. That's how it works. There are a bunch of use cases internally. We're using it in MITRE to test analytics and to develop new analytics. We have so that's one of the primary aspects I think as network defenders. The idea of adversary emulation is to do adversary-like things and to see how your defenses respond. One of the other things you can do is if you just want like bad guy data, if you want to run something and see what happens, you can use Caldera. It's really great for that. And another thing that you might want to do if you actually have a red team or a blue team and you want to train them, it makes a little bit more sense for a blue team. You can put them up against an automatic adversary, and we have some timing configurations, so you can actually slow Caldera down if you want to be a little more fair to your blue team. You can do that. You can also use it to train, if you have like a bunch of new guys and you just want to show them kind of the overall flow and just give them something to look at, you could use Caldera for that as well. So the code, it's open source. The whole project is open. We want participation from the community. That's why we're presenting at Black Hat. We'll pretty much, anything that's reasonable, we'll accept. We pull requests, bug fixes. If you have new techniques, we have 30 or so techniques implemented, but if there are more, there are definitely more. And if you want to implement something and send us a pull request, we're open to that. Absolutely. And if you want to integrate Caldera with new frameworks, if you want to add APIs, 100% okay. And we showed you the data model. There's always more that you can add to that. So if you have an idea for a new object to add, open to that as well. There are a lot. Honestly, there's a lot of stuff happening in this area. I put a bunch of tools up here. This will be available. I mean, you can't really like type URLs from this slide, but there are a lot of tools available. We'll post the presentation, and you'll be able to, click on, visit some of these pages. There's some really cool stuff that's happening in this area. And I have to plug some of the other efforts that some of our co-researchers are doing. We have a project called Brawl that does automatic red bot versus blue bot cyber games. So Caldera is the red bot in this case. There are other blue bots that try to detect or prevent Caldera from doing stuff. We've publicly released a bunch of data. So this is all sensor data that's been collected of stuff that Caldera is doing. It's mostly Sysmon data, if you're familiar with that. And there are a few other efforts that we have in this area as well. So just to kind of bring it back up to the beginning, false negative problem, it's really hard. I mean, it's hard to know what you're missing. And I think one of the good ways that you can address this is by introducing a realistic emulated adversary on your network. It's kind of a really nice sanity check just to see what your network is vulnerable to. We didn't really talk about this, but it's important to mention that Caldera, we think it's really good research. It's cool that you can do this stuff automatically, but I don't know if it's ever going to be able to fully replace a human adversary. I mean, humans are creative. Humans can, make inferences. These are things that are really hard for a program to do, quite frankly. But that being said, Caldera is, you don't need a lot of smarts to set up and run Caldera, and it still does a lot of things and can give you meaningful output. But it does complement a human adversary, a human red team, pre and post conditions. We spent a lot of time talking about that. Hopefully we didn't bore you. I think it's really interesting. And if you get anything from this talk, it's that thinking about this problem as a planning problem can be really powerful. And finally, this is a difficult problem. We're open sourcing it because we think it can help the community and help us help you. So, and finally, this is the GitHub. This is the repo. Feel free to download the code and use it. So with that, are there any questions for me or Andy? I think there's a microphone coming down for you.
Thank you very much for making this open source. But I had a question with regards to the heuristic model that you're using. Twofold question. Why don't you have a cost function to the tools that you're using as well? Would that gain a better autonomistic person? maybe I can speak louder. So about the cost function in the heuristic model to make it better at being non-detectable for like certain capabilities like that a blue team would have. Also about a economic-like probit logic model to replace your heuristic model to do like a more forward-through game to attack model.
Yeah, so, can you guys hear me? Yep. So we looked a little bit into that. One of the papers that we have, we tried to incorporate, what do we do if there's like a defender looking for us? And the idea there, it was a very toy example, but the idea was like certain types of lateral movement are easier to detect than other types of lateral movement. And to be very blunt, it was easier to roll that into that reward score and say, I'm just going to try to do a full ordering of the actions with the reward score. Ideally, it would be better to say, I have a reward for executing this, and then I have a cost or a risk, which is, and then combining the two somewhere else as opposed to like immediately in that score. So we haven't looked into it like necessarily at that level, which is the right level. But we've kind of done a little bit of exploration there, and I think that might be some interesting research for us to go down.
Any other questions?
Do you actually dare to run this on a production environment? Because when I'm there with basic binaries, that kind of stuff,
Yeah. So, I would consider this a prototype. So I wouldn't like put this on your production environment. Yeah. Why not? I mean, the software, it's a prototype. We're researchers, so we don't like build products. So the quality of the software, it's as good as we can make it, but we're researchers, right? We don't have unlimited resources. With that being said, we've tried to make it as robust as possible. We haven't done like a complete, spent like thousands of dollars doing like an audit or anything. So, we've tried to make it as secure as possible, but no guarantees that, there's not something that we just missed. That being said, the code is open source. And so if anyone finds any problems with it, yeah.
Do you plan to expand to Linux?
Yes. Can't make any promises, but we do, yeah. Oh, so the question was, do we plan to expand to Linux? And the answer is, we can't make any promises, but we plan to. Is there another question over here? Okay. Yeah?
Earlier you said that Earlier, you said you can choose a target you want, so data exfiltration or maybe a denial of service. Can you show us what you will do to change this target?
Oh, to like specifically select the target?
Okay, I didn't see it. I'm sorry.
Well. So were you asking how you specifically select a target?
Yes.
Okay.
We're not quite at the level where you can specifically say like, go compromise this specific host. It's more of that.
So the way the system works is you give it all the capabilities and then it uses as many as it can. So it would be pretty easy to modify the software to put in a stopping condition. So like, if you wanted it to stop after it got to a specific host, you could just have it detect, in like a conditional statement, stop here. We haven't built that into the software, and that's because in our research, it's most useful to have the software just get as far as possible always. and compromise as many hosts as it can. So I don't know if that answers your question. But
Okay. Thank you.
I think one of you guys mentioned that you're doing research in AI, and I imagine, that's where we're going with this. Can you just touch upon what you're doing right now, or and perhaps where the roadmap is, where it's going?
Yeah, it's a little more along the lines of classical AI. We're not quite getting into that, fun reinforcement learning, AlphaGo, fun stuff. We've looked a little bit into stuff like that, but it's hard. But I think more, when we're using AI, we're taking a lot of stuff from the automated planning community, and that's kind of the big area we're looking to branch heavily into. Things like Markov decision processes, goal-based planning, again, different kinds of heuristics, things like that are our main kind of directions in that area. Another one is, being able to do better inference. Learning is possible, and not strictly in the reinforcement learning kind of category, but there's other things you might also want to try to learn, like maybe playing with the heuristic function. Can I learn a good function based on my, certain parameters or prior experiences?
I will say one of the problems in this domain is getting good data. So, I mean, if you want to do something like a learning-based algorithm, you really need hundreds of different examples of people's networks that have been compromised, and getting one of those examples is really hard. So that makes this field kind of extra challenging. I mean, it's not like you can just download 5,000 images of cats or something, so. Okay. Thank you.